Welcome to UGC lecture series Linear Integrated Circuits. In this lecture, we are going to discuss about the sine wave oscillator, in which RC phase shift oscillator, its frequency of oscillation, derivation of frequency of oscillation, and design of RC phase shift oscillator. This RC phase shift oscillator is a linear electronic oscillator that produces the sine waveform. It consists of an inverting amplifier. If you look at the circuit diagram, it consists of an inverting amplifier and 3 RC networks. The signal is given to the negative terminal of operational amplifier. So, it is the inverting amplifier. It produces 180 degree phase shift, and we know that the oscillator has to satisfy the 2 Barkhausen criteria simultaneously. That is, one is A beta must be greater than or equal to 1. The next condition is the phase shift in the loop A beta must be equal to 0 or 360 degree. So, this inverting amplifier produces 180 degree phase shift at its output. Since the input signal is given to, the feedback signal is given to the negative terminal, and the circuit is having 180 degree phase shift now. So, we have to produce another 180 degree phase shift, so that the entire phase shift will be equal to 360 degree or 0 degree to generate the sine wave output. So, for that we have connected RC pairs of 3 combinations, that is 3 stages of RC pairs. So, here that is the output voltage of the amplifier, and here you have to say this is the feedback voltage. This is the feedback voltage, called this as Vf, and this is the output voltage of the amplifier, inverting amplifier. So, now these 3 stages of RC combination is going to produce 180 degree. Each stage gives you 60 degree phase shift. So, this one stage R and C combination, this produces only 60 degree phase shift, and if you have 3 stages of R and C combination, then you will have 180 degree phase shift from the input to the output. So, here it is the output is started at 180 degree for 3 stages of RC pairs, and for single stage it is the output is starting at 60 degree. So, there is a phase difference between the input and output as 60 degree here for single RC stage. So, in order to obtain 180 degree phase shift, 60 plus 60 plus 60, so you have to have 3 RC stages to produce 180 degree phase shift. So, when you look at this graph, the input and output have the phase difference 180 degree. So, by this concept, in the RC phase shift oscillator, we have connected 3 stages of R and C. So, here we have to calculate this feedback voltage Vf, and this feedback voltage is given as the current through the resistance R, and it is multiplied with R. Say this current is I3. Now, we have to calculate this I3. So, I am redrawing this circuit to calculate the I3 current. If we calculate I3, we can calculate what is Vf. Vf is the voltage given fed back to the negative terminal, and if we calculate Vf, and finally we can calculate what is the frequency of oscillation as well as what is the gain of the amplifier, and beta is the gain of the feedback network. This is the feedback network here. These 3 RC stages gives you the feedback network, where we can calculate what is beta. Beta is now the output voltage divided by the input voltage. Here for the feedback network, what is the output voltage? It is Vf, and input voltage it is Vo. This is the input, this is the output. To calculate the gain of the feedback network, that is beta, it is the output by the input, Vf by V naught. So, I am redrawing the circuit of the feedback network. So, I am drawing here the feedback voltage, and here output voltage, and all the capacitors are equal, all the resistors are equal. Consider the current flowing in this loop is I1, the next loop has I2 and the next third one has I3. So, from this we have to write an equation for 3 loop. For the first one it is I1 which is flowing through the resistor and the capacitor. So, it is the series combination of resistor and capacitor. So, I am taking this I1 into R plus 1 by Cs minus this R is common to the second loop as well as the first loop. So, in the second loop through R I2 is also flowing. So, I am subtracting this I2R here and there is no I3 in this loop. So, put 0 for I3 is equal to the voltage V out. And for the second loop it is the current I1 is flowing through this resistance R. So, I am subtracting this I1 current through the resistance R and I2 is the current flowing in this loop. So, I2 into there are 2 resistors. So, 2R plus this capacitor 1 by Cs. So, wherever you have a capacitor, so in order to calculate the frequency you have to include the term called S, and if it is S you have to take it as 1 by Cs. And what is I3 in this equation? Here this resistor is taking the current I3 also. So, I am subtracting this I3 R equal to 0, there is no voltage. And finally, the third loop has I2 current, there is no I1 current. So, 0, I2 current is flowing through this resistance. So, subtract the I2 current flowing through the resistance I2R plus I3 is flowing through 2 resistors. So, 2R plus 1 by Cs is equal to 0, again 0 here. Write this equation, then it is easy to calculate what is I3. Now, there are 3 equations. From this you have to write the matrix, and by using the matrix method we are going to find out the current I3. So, this is the coefficient of I1, or I am taking LCM. So, R Cs plus 1 by Cs, and coefficient of I2 is minus R, I3 is 0. And for the next equation I1 is minus R, I2 is 2 R Cs plus 1 by Cs, and for I3 it is minus R. And for the last equation I1 is 0, I2 is minus R, I3 is 2 R Cs plus 1 by Cs. And here I1, I2, I3 is equal to V0, 0, 0. So, if you multiply these 2 matrices, then you will get this equation. So, this equation now it is replaced by the matrix method in order to find out the equation for I3. For that, I3 is actually equal to D3 by del. Del is the determinant value of this particular matrix, and D3 is the determinant value of the matrix with the third column replaced by the output, this voltage 0, 0, the third column replaced by that. So, now we find out what is I3. For that we have to first calculate the determinant value of this matrix. So, del is equal to, we know the matrix multiplication. So, it is R Cs plus 1 by Cs into these two terms, it is 2r cs plus 1 by cs the whole square minus r square. You have minus here, so put plus r. So leave this particular column and this particular row. You have minus r into 2r cs plus 1 by cs. Now you have to multiply the term and you have to take this cs out. So when you square the cs, you will have here c cube s cube out. Similarly here, if commonly you have to take c cube s cube out, and finally you multiply inside, you apply the theorem a plus b the whole square. So you will have a square plus b square plus 2ab. First you expand this, then you multiply this term 1 plus RCS inside, and then finally you will get an equation like 1 by c cube s cube into r cube c cube s cube plus 6 r square c square s square plus 5 r c s plus 1. So once you simplify this equation, you will get the determinant value like this. So this is your del value. For I3, it is actually d3 by del. And what is d3? d3 is, in this matrix, you have to replace the last column as V0 0 0. So you will get the matrix as RCS plus 1 by CS minus R V0. So the last column will be the output of the equations. The remaining columns are as such. So here minus R, here 2R CS plus 1 by CS, here 0, here minus R. So this is our D3. We have just replaced the last column as the output voltage. And now if you calculate D3, it is, you will have 0 here. So first if you take this term, you will get 0, and this term also you will get 0. The final term V0, if you take, then it will be R square. So D3 is V0 R square. So I3 will be now V0 R square by del. So del is this. You have to substitute this equation here for I3. I3 will be equal to V0 R square, V0 R square. Here this will be coming to the numerator, c cube s cube divided by everything in the denominator. It is r cube c cube s cube plus 6 r square c square s square plus 5 r c s plus 1. And we know that s is equal to j omega, s square is equal to, j square is actually minus 1. So you will have minus omega square, and s cube is another j omega, you have to multiply with this. So you have minus j omega square. If you substitute, okay, you keep these things in mind. Now we have only calculated what is I3, but we have to calculate beta. So Vf is I3 into R, Vf is I3 R, and beta is Vf by output by input. So now for the feedback network, the output voltage is Vf and the input voltage is V0. Now you substitute this Vf. Vf is actually calculated through this I3R. So here I3R, if you multiply this I3 into R, that will be your Vf. So V0 R cube C cube S cube. If you multiply R square with this R, you have R cube divided by r cube c cube s cube plus 6 r square c square s square plus 5 r c s plus 1. This is your Vf divided by V naught is also there. So, include V naught in the denominator. So, this V naught will get cancelled. This is your beta now. Now, you substitute S is equal to j omega, these values in this equation. You have beta is equal to S cube will have minus j omega cube. So, minus j omega cube r cube c cube divided by, here also you will have the same value j omega cube r cube c cube, since you have s cube terms, plus 6 r square c square. For s square you have omega square, you have a minus omega square. So, here you replace the plus as minus, it is minus, and here you have only s. So, you will get 5 r c j omega plus 1. So, now you multiply, you divide this term, divide minus j omega cube r cube c cube, divide this term in the numerator as well as the denominator. So, you will be getting beta is equal to, if you divide and if you substitute alpha is equal to 1 by omega RC. Once you divide this and you substitute alpha is equal to 1 by RC, you will get beta is equal to 1 by 1 minus j 6 alpha minus 5 alpha square plus j alpha cube. So, you have 1 by 1 minus 5 alpha square minus j into, you have 2 j terms. So, here you have 6 alpha minus alpha cube. So, now this is your beta. So, beta is 1 by 1 minus 5 alpha square minus j into 6 alpha minus alpha cube. This is beta, right. So, we know that the magnitude of A beta must be equal to 1, equal to or greater than 1. This is one of the Barkhausen criteria. So, in order to make this beta to be real, we have to consider the imaginary term equal to 0. So, if you take this imaginary term to be equal to 0, you will have 6 minus alpha square equal to 0, and alpha square is equal to 6 alpha is equal to root 6, and beta will be equal to 1 by 1 minus 5 into alpha square. If you make this root 6 square, you will have 6. So, you have 1 by minus 29. This is your beta value. This is where 1 by 29 is your beta value. So, what is the value of A in order to satisfy this condition? So, A must be equal to, greater than or equal to 29. So, for this RC phase shift oscillator, when you look at the circuit, it is the inverting amplifier, and A is the gain of this, inverting amplifier. So, what is A now? A is R2 minus R2 by R1. Inverting amplifier gain is the feedback resistor divided by the input resistor. So, minus R2 by R1 must be greater than or equal to, you have minus minus 29. So, R2 must be greater than or equal to R1. This is the must be greater than or equal to 29 times R1. This is the value of the resistors in the inverting amplifier. R2 will be greater than or equal to 29 times of R1. So, this you have to concentrate while designing. And what are the other values you have? So, we have derived the magnitude, we have satisfied this condition, and finally, we have to derive the frequency of oscillation. So, how will you calculate the frequency of oscillation? Alpha is equal to what? It is 1 by omega RC. We have assumed this as 1 by, we know that alpha is root 6, and from this omega you can calculate what is the frequency. Omega is equal to, if you take this here, it is 1 by RC, alpha is actually root 6. And what is omega? Omega is 2 pi f is equal to 1 by RC root 6. So, f is equal to 1 by 2 pi RC root 6. This is the frequency of oscillation for the RC phase shift oscillator. So, we have derived the frequency of oscillation as 1 by 2 pi RC root 6, this, and the gain of the amplifier as A greater than or equal to minus 29, and these are the two important values for designing the RC phase shift oscillator. Next is design of RC phase shift oscillator to oscillate at 100 hertz. So, here if it is given as 100 hertz, then f is given, f is 100 hertz. And what is the formula? It is just now we have derived as 1 by 2 pi RC root 6. So, in this formula, assume the value of the capacitor C as 0.1 microfarad and calculate what is R. And one more thing we have to consider is, from the circuit, this resistance R1 must be 10 times of this R. This R1 must be 10 times of this R. So, R is calculated now from the frequency. R is calculated. For example, if this value is 6.5 kilo ohms, then R1 must be 10 times of R. So, it is 65, sorry, this is, yeah, it is 65 kilo ohms. R1 must be 10 times of R, and we know that the gain of the amplifier is, it must be greater than or equal to 29, the mod value. So, RF, that is R2 must be greater than or equal to 29 times of R1. Here this is the feedback resistor, this is the input resistor. So, these are the formulas which we have to remind during the design of the RC phase shift oscillator, which we have to remember during the design of the RC phase shift oscillator. And in this lecture we have seen what is the RC phase shift oscillator and what are the Barkhausen criteria, derivation of the frequency of oscillation, and design of RC phase shift oscillator for 100 hertz. Can you answer these questions? What is an oscillator? List the audio frequency and high frequency oscillators, define Barkhausen criteria, and design the oscillator, RC phase shift oscillator for 1000 hertz. So, in this list the audio frequency and high frequency oscillators is, audio frequency is RC combination of oscillator, the oscillator which uses RC pair, then it produces audio frequency. So, here we have discussed RC phase shift oscillator. This RC phase shift oscillator produces oscillations for the frequency in the range of 100 to few hundred kilo ohms, and if the oscillator is making use of L and C, then it is a high frequency oscillator. Hundreds of megahertz can be generated using this L and C pair of combination in the oscillators. Thank you.